We're going to start with a optimization problem. So suppose an open box is to have a fixed volume of 4 feet cubed. What is the minimum surface area possible for this box? Now, in Calc 1 we did these problems, and essentially these problems amounted to taking a couple equations and then doing some solving and such so that we can now write it as one equation that we need to optimize. We're actually going to have a totally different technique that we use in vector calc, which, might be easier in some cases. And that's going to involve Lagrange multipliers. So the short of it is that for a Lagrange multiplier, let x be an open set, because sometimes weird things happen on boundaries, and let f and g be functions of class C1 in whatever, vector space we're in. And let S be a level set satisfying g of x equals c. So we've seen level sets. You can think like a sphere is a level set, x squared plus y squared plus z squared equals 1. That's a level set. So this would be a level set satisfying g of x, x squared plus y squared plus z squared equals c, 1. And let f slash s denote f restricted to the level set. If f restricted to the level set has an extremum at x0 such that the gradient at x0 of g isn't 0, then there is a scalar lambda such that the gradient of f of x equals lambda times g of x. That's actually the gradient of g of x. Sorry. Now that sounds, why on earth would that be helpful for us? Well, what that's going to do is that's going to actually give us a system of equations that we can solve to handle these objective functions and these optimization problems. So let's go ahead and find our objective function, find our constraint equation, and then we're going to use this idea of Lagrange multipliers to set up a system of equations. So we're trying to, our objective function, what are we trying to optimize? We're trying to optimize the surface area. We're trying to minimize the surface area. Typically f is going to be what we're trying to minimize, because as you see here, we are finding where f restricted to s has an extremum, so f is what we're minimizing. So we're going to have f of, might as well just write x, y, z, because we have 3 variables x, y, z, according to my little picture here. What's the surface area of this box? Well, we're going to have 2 sides with dimensions xz, so we have 2xz, 2 dimensions with sides yz, and since it's an open box, it's only going to have 1 dimension with length xy. What's my constraint? Well, we know this has a volume of 4. So my constraint equation is going to be xyz equals 4. This means that we have a level set, just thinking ahead. We're looking at a level set of g of x equals 4, where g of x equals xyz. So we have our 2 functions, f of xyz equals 2xz plus 2yz plus xy, and then g of x, gx, or g of xyz I could have written equals x times y times z. Now, what's this going to say? We know that the gradient of f, let's go ahead and find these things. The gradient of f is going to be, well, the partial in respect to x is going to be y plus 2z. Partial in respect to y is going to be x plus 2z. And the partial in respect to z is going to be 2x plus 2y. The gradient of g is going to be yz, xz, xy. So if you look at what this is telling us, at an extreme value, so at our minimum surface area, satisfying the constraint equation, That's basically saying f restricted to s is minimized. We have an extremum of f restricted to s. We know that the gradient of f equals lambda times the gradient of g. Or maybe the gradient of g equals 0. We should check that, because this said if there's an extremum such that the gradient of g isn't 0. So we should check. But what that lets me do is that tells me, and I'm going to set up a nice system of equations here. That tells me that y plus 2, if we look at component by component, y plus 2z has to equal lambda times yz. Also, x plus 2z has to equal lambda times xz, and 2x plus 2y has to equal lambda times xy. And you'll notice I left room for one more constraint, and that is, spoiled it, I left room for one more equation, which is my constraint equation. We also need to satisfy that xyz equals 4. And this gives me a system of equations that I can solve. Or, as I said, we might have this case, or we might have that the gradient of g equals 0. So whatever our extremum is, it has to satisfy one of these two things. Let's start with, just to get it out of the way, start with the gradient of g equals 0. Is that possible? Well, that's going to happen. This happens at, we look at the gradient of g, it's yz, xz, xy, and you can convince yourself that at least two of the things need to equal 0 for the gradient to equal 0 at a place where I can even say at least one variable equals 0. Which fails our constraint equation, which does not satisfy our constraint equation. Okay, so we can ignore that case. Now we can just focus on solutions to our system of equations. And there's a couple ways you can do this. One thing that's often helpful is to solve for lambda. So I'll box that off so we're not thinking about it anymore. We'll solve for lambda in one of our cases. Maybe this one because it's nice and symmetrical. So we have lambda of xy equals 2x plus 2y. That's going to get me that lambda, if I divide both sides by xy, is going to equal 2 over y plus 2 over x. So what we can do, first of all, we should note that y and x can't be 0 because, of course, that would fail our constraint equation. So that's good. And what we can do is we can actually substitute that into some of our other equations. So we have this. Now we can look maybe at our first equation and see what happens when we substitute that in. We are going to get y plus 2z equals 2 over y plus 2 over x times yz. That's going to get us y plus 2z equals, let's see here, we're going to have 2z plus 2yz over x. I notice that those two z's are going to cancel out. That's nice. So I'm going to get y equals 2yz over x. And we can go one better. We can go ahead and cancel out some y's. We're going to get 1 equals 2z over x, or x equals 2z. Okay. Since that worked out so nicely, let's just do the same thing for the second equation and see what we get. We're going to get x plus 2z equals lambda times xc, but lambda is 2 over y plus 2 over x times xc. That's going to give me x plus 2z equals, let's see, that's going to give me 2xc over y plus 2z. Once again, the 2z's are going to cancel. We'll get x equals 2x over y. And by the same shenanigans we saw earlier, 2xc over y, we're going to get 1 equals 2z over y, or that y equals 2z. So we have x equals 2z, y equals 2z. Now I can go over to my constraint equation and plug those two things in. So I'm going to have x, which is 2z, times y, which is 2z, times z equals 4. That's going to be 4z cubed equals 4. Obviously, we need to have positive values, so, well, it doesn't matter if we have positive values, it's just z is going to equal 1. So we have z equals 1. And then since x and y each equal to z, we're going to end up with x equals 2 and y equals 2. And those are going to be the dimensions that minimize our surface area. We might want to put units on those. That's going to be minimum dimensions, or minimizing dimensions, I'll say, are 1 foot by 2 foot, or well, we should go x by y by z. That's going to be 2 feet by 2 feet by 1 foot. And if we really wanted to, we could even calculate what the surface area is going to be. Probably going to end up being something like 12. So yeah, our surface area is going to be 12 feet squared. So we'll have 2 times 2 times 1, 2 times 2 times 1, and then 2 times 2. And that is the solution to our optimization problem.